Okay, so after talking about the operations on the tenses, let's talk about the operators of the tenses. Alright, what is sub in into the matrices? Okay, I'm not going into details on how to sub in. Alright, I'll just briefly talk about what are all these things all about. Alright, so to start off, if you remember back to our operations of tenses, if I have u dot v, I'm simply putting this as dot. If I have u cross dyadic v, I have this form. If I have u cross v now, I have this one. And then I'm simply group the u and the v's together. Alright, these are all v's. Sorry, these are all v's. Alright, and therefore if I were to group all the v's together, the u's and the v's, I would say, the rest is simply working on the basis vector. Right, as you can see what I'm writing right now. So the trend are all the same, and the key players is actually the basis vector. Alright, and now in operators of vectors or operators, tensor operators, the key player now, instead of just the basis vector, I will call this the del operator. Okay, the del operators is simply if you were to differentiate, alright, each of the so-called the basis vector, if you were to partial them in terms of their own directions. Alright, so therefore partial e2, partial y, and partial e3, partial z. Alright, this is simply the del operator. And you will soon see that del operator is used throughout the divergence, the curl, and the gradient of the vector field. Okay, my definitions of the del operator, as you can see, is if you were to look into the typical drawings, alright, the typical drawings, if I have a direction space, I have a certain space, alright, and I have maybe I shouldn't write in green color because I always represent my basis vector as green. Okay, so this is some space, alright, and then I have the basis vector with magnitudes 1. Alright, this is e1 hat, this is e2 hat, e3 hat. So for del operator is simply dealing with how do I say, because we know that basis vector is the key player in the game, as from the operations over here, right? Operations over here. So we know that the basis vector is very important, and therefore if you were to subject things in terms of dynamic, meaning changing in time, alright, normally what change in time is the position of a body. Alright, for example, a body is this. Across a certain time the body may be deformed, alright, maybe not small but rather deformed into a different shape. So we are very keen to know the position and the time. Alright, so we're gonna differentiate in terms of its position, alright, in terms of each of its directions. This is what it's doing. Alright, so this is differentiated across each of its own direction. Yeah, I'm not going into details on how it is, but I'll just emphasize on del operator is very important, and how del operators is being operated is through this one. Alright, so this is simply the del operator. If I were to zoom in a little bit, they didn't include the basis vector, the e1, e2, they just simply write this as this. This is the del operator. So del operator is denoted by the inverted triangle over here. And then for gradient, alright, the gradient is what you get when you multiply del by a scalar function. So f itself is some scalar function. Alright. What is a scalar function is simply any functions that represents x and y or z. Alright, maybe 2xy plus x is also a scalar function, or z square plus 2xy is also a scalar function. Alright, so this function itself is just any function that you can think out of x, y, z. Alright, so this is the gradient. Alright, and this is the outcome for a gradient. Alright, it's simply the operator times the scalar function. That's the meaning of that. Alright, the divergence, on the other hand, is the del operator dot product with the vector field. Alright, with a vector field. So a vector field in this case is, in other words, the vector itself. Alright, so as by definition, the gradient itself is just a scalar 2xy plus y. It's some function. For this f is just some vectors. Alright, some vectors, maybe 3, 2, 1 is a vector. Alright, here and there. But the vector f, okay, I want to convey over here, can be rewritten as this form. Right, PE1 QE2 hat plus RE3 hat. Alright, each of them spans each of the basis vector also in another space, I would say. Alright, so these are the components. So it's PQR. Alright, so therefore the where am I? The divergence itself is simply the del operator multiplied by the vector f. And that's all, and then you do your own stuff. Alright, as for the curl itself, is the del operator times the cross product with the del. Alright, so as you can see, we are simply using the operations that we have derived in the past videos to do with our operators right now, right? So the operators is simply the del operator, right? And del operator x dot product, cross product, or just simply multiplications, alright? And you get different stuffs out of it, alright? And you can go to this video, Gradient, Divergence and Curve by Jason Rose. And then it's a very short video that touches on all of this calculation. Alright, it's a very short and quick video, which is very great. Alright, and before I off this thing, I just want to convey certain information, which is how does the gradient and the divergence and the curl applies. Alright, you may have all these definitions, but in terms of applications, there is a need for this to happen, right? Otherwise we wouldn't want to apply this, right? And therefore for curl, alright, it deals with the fluid itself. If a vector field represents the flow velocity of a moving fluid, maybe air, maybe water, or whatsoever, alright, or heat, alright, so as you can see, it's some rotational stuff. And as you remember, the magnitude is dependent on the length of the vector, as you can see, alright. So the length of the vector will determine how powerful the magnitude it is. Similarly to the gradient itself gives us the understanding of let me see, on the values, alright, on the higher. So as you can see in the above two images, the values of the function are represented in black and white. The black represent higher values, while the white color is the lower values, alright. So therefore, as for divergence, it's just simply a similar concept. I'll not go into details on how they are similar and things like that, because I also don't know how it is. But anyway, what I want to convey is, if you remember SolidWorks, you see all this color, green, blue, yellow, red. These are in fact the works of divergence, gradients, and if you were to go into those like heat transfer stuff like that, you'll get to know that the heat source, or the heat analysis for or thermodynamics or heat transfer of a certain analysis on SolidWorks. As you can see, the gradients itself are all talking about that, and the curl, alright, as you can see, the curl are all present in this picture itself. So as you can see, the curl, the gradient, and divergence are all the tools for us to set up the understanding for all this analysis in the real world. And therefore this is the thing that I want to convey, and if you want to know how to calculate, you just click this video and check it out. Alright, so I think this is it. So in the next video I'll just do out a quick summary of the whole thing on tensors and vectors and things like that. So see you there.